Here is a spring in its equilibrium position. It's hanging vertically. It is neither stretched nor compressed. We add a mass m to the spring, which of course causes the spring to be stretched by a certain amount. So let's say that the spring has been stretched by some amount L. Now this mass is in equilibrium, so it's resting here in this position. We haven't set this mass in motion, but even if we do set it in motion, we can still consider the forces acting on M when it's, say, passing through this position. We have its weight, which is acting vertically down. That's mg. But because it's in equilibrium, we have an equal and opposite upward force. This is the force on the mass due to the spring. And we know by Hooke's law that the spring force is proportional to the extension of the spring or the compression of the spring. But here we're dealing with the extension of the spring, and the spring has been extended by L meters. So the magnitude of the spring force is the spring constant K multiplied by L. So we're just looking at magnitudes here. So forget about putting a minus sign in here to get the signs and all that right. If we're looking at magnitudes, we want this force to be positive. K is a positive number. It's the spring constant. Depends on the material that the spring is made of. K is always positive. Some fixed number for a particular spring. And L is some positive number here. We're assuming that L is just the extension of the spring. So L is a magnitude. So the magnitude of the spring force must equal the magnitude of the weight. Well, the magnitude of the weight is mg. Mg is of course always positive. M is positive, G is positive. Now we are going to call the equilibrium position of the mass m x equals 0. And we are interested in displacements of this mass in the vertical direction. So we need to look at the upwards direction and the downwards direction. So we have to make one of those directions positive. Let's make the upward direction positive. And then of course the downward direction will be negative. But of course we could reverse these directions and it won't make any difference. But we have to decide at the very start what convention to use. Now let's suppose that this mass has been set in motion and that it's in some position here, say later, sometime t later, say it's here. So the mass has been set in motion. Well, you could do that by pushing the mass up and releasing it, or pulling the mass down and releasing it, and it will oscillate up and down. And at some time, it's, say, in this position here. And we are interested in the forces acting on it when it's in this position. So the equilibrium position is represented by this horizontal dotted line here. That's the equilibrium position for the mass. Well, actually, since the mass is assumed to be a point mass, we're looking at the position of this end of the spring. The position of this end of the spring initially, before the mass was attached, is given by this horizontal dotted line here. And the distance between these lines is L. Let's look at the forces acting on this mass. Well, we have its weight, which never changes for masses near the surface of the Earth. Weight is constant, mg. But the spring force will depend on the extension of the spring. It will depend on the extension of the spring from its equilibrium position, which is here. It will depend on the distance from this point to this point here. Notice that when the mass is below its equilibrium position, then the spring force, the magnitude of the spring force is actually greater than the weight, because the spring wants to restore itself to its original length. So the resultant force must be upwards for that to happen. So that means that F spring must be greater in magnitude than mg. What is F spring? Well, we know that the magnitude is given by constant k times the extension of the spring. The extension of the spring is the distance from here to here. So we have this horizontal dotted line here, which is at some position x. So x is some negative number in this situation. See, the mass is below the equilibrium position, and positions below are assigned negative values. But the equilibrium position of the spring is given by L. L is some positive number. To find the distance between two numbers, this distance here, we just subtract them. So we just take L and subtract x. That will give us the distance. Well, if we want to ensure that this comes out to be positive, we can put vertical lines on either side. So the magnitude of L minus x is the distance between the numbers L and x. L is some you could think of L as a positive number. It's the equilibrium position of the spring. See, it's above x equals 0, so it's positive. Whereas x for this position is negative, because m is below the equilibrium position. Anyway, we just subtract the numbers, and that's how we get the distance. And just get the absolute value or magnitude to make that positive, because we want the magnitude of F spring here. We want that to come out to be positive. But you see here that for this situation, L is greater than X. L is here, X is down here. So we can drop these vertical lines if we want, and just use brackets, because L is greater than X. So L minus X will be positive. L is greater than X means L minus X is positive anyway, so we don't have to put those absolute value lines in. So that's the situation here, and later we will cover the situation where L is less than X. That's the case where the mass, say, is up here. That could happen. Well, it doesn't necessarily have to happen, but it could happen that if the mass was given a sufficient enough displacement at the start, it could oscillate up and down between points, well, up to one point anyway, which is above this horizontal line here. Now let's look at the magnitude of the resultant force acting on this mass. Well, we have the spring force, which is KL minus KX, and we have the weight, which is mg. So the weight is in the negative direction. So we have KL minus KX minus mg. But we already know that KL must equal mg. So if KL equals mg, then KL minus mg will give us 0. So here is the resultant force. Actually, we don't just have the magnitude, well, we have the vector F. We don't have the magnitude. Although we do have the magnitude, because x is negative here. We have a negative times a negative, which gives us a positive quantity. So we could say we have not only vector F, but we have its magnitude, because vector F comes out to be positive when the mass is in this position here, when it's below its equilibrium position. But anyway, in general, vector F is minus k times vector x. These cancel, of course. So that's the situation here, and I will show that this formula also works for the mass m in other positions. Well, here we have the case where L is greater than X. We get this formula here, and it also works, by the way, if the mass happens to be up here. x will be positive. And the resultant force will be negative. Okay, because F and X point in opposite directions. So when X is positive, F has to be negative. You can see that the resultant force has to act in downwards when mass M is above the equilibrium position. Now let's consider the case where the mass is in this position. So this horizontal line is x equals 0. This position here is L, x equals L. L is some positive number. And you can see that x is greater than L, or L is less than x, same thing. If L is less than x, then L minus x will be negative, it will be less than 0. So what are the forces acting on the mass in this position? Well, we still have its weight, of course, mg. It's constant for a mass near the surface of the Earth. We also have the spring force acting. Now, in what direction is the spring force acting? Well, the spring force acts in a direction to restore the length of the spring. So the spring, this point on this part of the spring wants to get to here. So the spring force must be acting downwards. Of course, it could be greater than the weight. Here I'm showing it less than the weight, but whatever. So the resultant force is the sum of these two vectors. So the resultant force must be pointing downwards. We could just add the magnitudes of these vectors together to get this resultant force vector. We know by Hooke's law that the magnitude of F spring is the spring constant K, which is positive, times the magnitude of L minus X. So L minus X, as I said before, is the distance between point L and point X. So this distance here is the extension of the spring, or the compression of the spring in this case. The spring is not extended, it's actually compressed. It's compressed by this amount here. So to find this amount, we subtract the two values. We take L and we subtract X, but we get the absolute value or magnitude, so that this comes out to be positive. And of course K is positive. K is always positive. So the magnitude of F spring is this here. So the magnitude of the resultant force is K times L minus X plus mg. This is the magnitude, so I've added this magnitude onto this, and we can do that because the two vectors are pointing in the same direction. So we get this longer vector. Now, we are interested in not the magnitude of F, but vector F itself. We want to show that it can be given by this form here. So we need to see that F spring and mg are both negative vectors. So we're interested in vector F spring. Well, that has to be negative because vector F spring is pointing downwards. So what do we need to do to this to make it negative? Well, we can just drop the absolute value lines because L minus X is negative anyway. So we just put K times L minus X in round brackets. So this will come out to be negative, which is what we want actually. And we just put a minus sign here to make this, to indicate that this vector is mg is negative. That's a vector pointing downwards in the negative x direction. So now we have the resultant force vector, and it should break down to this form here. Well, we know that KL is equal to mg. So vector F is KL minus KX minus mg. KL equals mg, so we get 0. So vector F equals minus K times X. And we can put a vector sign on X, and we'll see that this thing here will make sense for when the mass is in this position here, because you see that X is positive. Okay, the mass is above the equilibrium position. Minus K, as I've said many times before, is always negative, because K is always positive, so minus K is always a negative scalar. So we have a negative scalar times vector x. Well, that will reverse the direction of vector x. So a negative times a positive gives us a negative. So vector f must be negative, and indeed it is. The resultant force is indeed negative. It's pointing downwards. So this formula checks out for all positions of mass m. So you see it's got the same form as for a mass on a horizontal spring. For a mass on a horizontal spring, as you saw in the previous video, F is also equal to minus k times x. So even with this extra complication of mg, we still have this form here, which is convenient. As I said before, we can drop these arrows because all the vectors are in one dimension, in this case the vertical dimension. So the signs of f and x give us the directions of vectors f and x. But you always have to keep in mind that f is actually a vector. It can be positive or negative. And x is a vector. It can be positive or negative. This minus k is a scalar.